Thank you, Cha, for the introduction. Good morning, everyone. In today's talk, we approach the problem of computing and visualizing derived quantities in FEM simulation data. This is the visualization of data from the simulation. What is the problem with the visualization? The data looks non-smooth and inconsistent with the physics. The reason the data looks non-smooth is because of the discontinuities. These discontinuities have helped in algorithmic and mathematical advancement in the simulation, but create visual artifacts when you are trying to visualize the data. These discontinuities exist in higher order finite volume data, commonly known as DG data. In case of higher order finite element data, commonly known as CG data, the data is continuous at element boundaries, but the moment you take a derivative, the data becomes discontinuous. So where did this data come from? These data has come from larger D simulations. The larger D simulations help in understanding the formation and evolution of the wingtip vortex. These simulations also help understanding the fluid behavior around an aeroplane wing. These vortices are hard to simulate due to the high Reynolds number required. Lombard et al. In 2015 was able to simulate this data very close to the experimental data. And this is the image used in the paper. So the natural question is, how did they get such a nice continuous image for the data? So we asked them, and they've informed us that they averaged the data. So when they did an average, they introduced some kind of error into the visualization data. But in this talk, we highlight the problems with the current techniques and tools used in visualizing simulation data, introduce line-SIAC filter, and demonstrate that line-SIAC filter is an effective tool to accurately visualize the derived quantities and the simulation data. So now let's understand visualization from the simulation pipeline. This is a simulation pipeline in computational engineering and science. So the simulation scientist builds a mathematical model for the physical process he is interested in, and then uses techniques like finite elements, finite volumes to simulate the data, and as a last step, post-process the data for visualization. In the literature, the scientist normally uses some kind of validation and verification to gain confidence in the error estimates and the simulation data. But there is no verification done normally for post-processing of data. In 2008, Kirby and Silva advocated that if visualization is the lens through which the scientist visualizes data, then visualization needs to be included into the verification pipeline. So what this means for us is the visualization data needs to be accurate as simulation data and be consistent with the physics. So now let's look at the finite element measures and the data to understand more about the problem. In traditional or linear finite elements, the data is stored at the vertices, and we have straight edges, and the data is interpolated at anywhere inside the element. In case of higher order finite elements, you have curved edges, and the data is stored in the polynomial space. So one way to store the data in the polynomial space is to store the data at more than the vertices. And when you try to visualize the data on the higher order mesh, you can clearly see the discontinuities in the data. But the visualization tools we have currently are designed to visualize linear and continuous data. So what did people do to visualize this data? One way they visualized this, they sampled the data on a fine grid and then visualized it. And the next one is they've subdivided the mesh into smaller elements and then input the data, sample the simulation data, and input it into softwares by kitware to visualize this data. Recently, Elvis is a software which uses ray tracing and root finding to do a pixel exact visualization of the simulation data. All these methods either have interpolation errors or visual artifacts. And these problems become worse when you try to calculate derived quantities from the simulation data. The idea we propose is to reconstruct the solution while conserving the accuracy. For this, we use SIAC filters SIAC filters have been introduced in the math community by Cogburn et al. In 2000. They stand for smoothness increasing, accuracy conserving filters. These filters have been mathematically proved to conserve accuracy, increase the continuity between element boundaries, and have a higher convergence rate. This is a result of using SIAC filter on a 2D problem. It is important to note here, filtering done in this context is different from signal processing filter. In some sense, this filter is specially built for finite element simulations. So let's look at a 1D SIAC filter to understand it better. So let's say UH is a 1D FEM solution of our polynomial order k plus 1. KH is the SIAC kernel, where H is the characteristic length of the SIAC kernel. When we convolute the SIAC kernel with the FEM solution, you create U star, which is the post-process solution. This solution has polynomial order 2k plus 1 and has continuity at the element boundaries, which is k minus 1. So the SIAC kernel is a linear combination of B-splines, and in this image we show the SIAC kernel in the dotted black line, and the red lines are the B-splines used to construct the SIAC kernel. The interesting part of the SIAC kernel is the characteristic of the SIAC kernel, which states that if you convolute the SIAC kernel with monomials up to degree 2k plus 1, you exactly reproduce the polynomials. Now let's look at the SIAC kernel in higher dimensions. The SIAC kernel in higher dimensions is built using a tensor product of one-dimensional SIAC kernels, and these SIAC kernels are computationally difficult to be used because of the complexity of the SIAC kernel mesh and the simulation mesh you have. Recently, a new kind of SIAC filters known as L-SIAC filters have been published. These filters, the specialty of this filter is they use a 1D SIAC kernel and then apply it on a d-dimensional, and you can use it to apply it on a d-dimensional field. And the way you use it is you take the SIAC kernel, rotate in the direction you would like the filter to be applied, and then apply the filter. Naturally, you have two parameters. One is the characteristic length, and the other is the angle parameter. It is mathematically proven that all the properties of the SIAC filter also exist in the L-SIAC filter. Now let's transition into results to understand the current techniques versus using L-SIAC for calculating derived quantities and for visualizing the simulation data. So for doing the comparison, we take a flow path cylinder. The flow path cylinder is a canonical example which has all the interesting fluid characteristics. The mesh is a hybrid of quadrilaterals and triangles of polynomial degree 3. We use Nectar++ to do the simulation, and we simulated till the flow reached the transient state. And once it reaches the transient state, we took one snapshot of the simulation data. And now the goal is to calculate vorticity in the rectangular box. So if we first try to use it using FEM derivatives, and we can clearly see the discontinuities at the element boundaries. And the next one is to sample the mesh, sample the simulation data on the grid, and then use the data to calculate vorticity. You can clearly see the visual artifacts coming near the triangles and quadrilaterals border. The next one is to subdivide the mesh and then calculate the simulation data at the vertices of the new mesh, and then use this to calculate the vorticity. You can still see the visual artifacts. And when you compare these results to calculating LSIAC to using LSIAC to calculate the vorticity, you can clearly see the contours are continuous and there are no visual artifacts. To do the comparison again, we sampled the data along the black lines here, and we created the line plots. Here you can again see the discontinuities in FEM derivatives and the visual artifacts in case of sampling or subdividing the mesh. And the LSIAC result is continuous and doesn't have any visual artifacts. Now, let's understand the impact of SIAC line-SIAC parameters. So line-SIAC has two parameters. One is the angle and the other is the characteristic length. For the angle parameters, there are two ways we could have used it. One way, we could take the FEM vorticity and then apply line-SIAC. And we've realized there's a better way. The better way was to use line-SIAC to calculate the derivative quantities required for computing the vorticity. And then the line-SIAC derivatives, the derivative direction and the line-SIAC direction were aligned naturally. And the next parameter is the characteristic length. It's advised in the math community that the characteristic length is to be the maximum edge length in your simulation mesh. So we've used h here is equal to the maximum of the length of the quadrilaterals. And if we had used half the element length, the visual artifacts of the mesh start to come back. And if you used 1.5 times the advised characteristic length, then you get continuous solutions, but you're trading off accuracy at this point. So now let's come back to our larger dissimulation. So the idea is to use line-SIAC on the larger dissimulation data. So the goal is to calculate vorticity. Here we have a 3D mesh, polynomial degree 5, around 200,000 elements. And to do this comparison better, we take a small region along the vertex core trail, and here we represent the place by the green box here. And we can clearly see the discontinuities in the data. And if you compare this result with the line-SIAC, you can see line-SIAC has a clear isosurface, and now we take a 2D slice in this data represented by the black frame, and the iso contour represented by the yellow dotted line is continuous compared to the FEM vorticity. To do this comparison, we now visualize the 2D slices, and the yellow line in the previous slide is the red line in this visualization. We can clearly see the line-SIAC has iso contours which are continuous and concentric, and this is in line with how our understanding this is in line with how the physics looks for how the physics for the vorticity exists. In summary, we have highlighted the challenges in computing and visualizing derived quantities for the FEM simulation data. We've talked about the importance of verifiable visualization and introduced SIAC filter and demonstrated SIAC filter as an effective tool for visualizing higher order finite element data. We would like to thank Professor Spencer and Dr. Moxie and the whole Nectar++ group for the helpful discussions and providing us with the data. And we would like to also thank the other agencies for our support. Thank you.